Now I want you to look at example. This is also happens to be an example in Oppenheim and Schaefer. I want us to guess the magnitude response of this particular LTI system, which has got 3 poles and 3 zeros. 3 poles located at the points indicated here by the X's. The 3 zeros, all 3 are on the unit circle. 2 are close to the poles, 1 of them is far away from the pole. So as always, let us look at starting at omega equal to 0, looking at the response. So remember the poles, if you get close to a pole, what will happen? It will push the magnitude response up. So you start at some point, okay, we start at some point. As you move away from the pole, the whatever value you started from will droop a little bit. By that time you come closer to another pole, it will rise up again, but it does not rise very far because there is a 0 that is coming soon after that. The transfer function will come down here. Okay, this is the due to the first pole. This is the pole at omega equal to 0. This is the second pole, effect of the second pole, and this is the effect of the 0. Effect of the 0. Okay. And then what happens? The effect of the 0, then you go away from the 0, so slowly starts to increase, but eventually when it comes to omega equal to pi, it will drop down. So this is at pi. Okay, so you can see how the magnitude response is going to vary. Okay. And of course, once you have the magnitude response, you can also go through and look at the behavior with respect to phase and group delay. I'm going to, these you can verify. You can look at the example that is given in the textbook. I want you to focus on the magnitude response here. Okay. Now, supposing I had introduced another 0 here. What would be the change in the magnitude response? In the initial part, there won't be much change. In this part, what will happen? You will see that there will be another 0 here, and then it will go up, and again you will see a 0 here. You can see how you can modify the magnitude response by placing zeros at strategic locations. Now, if you had removed both the zeros, okay, supposing you had only this. Okay, you had the 3 poles, okay, you had the 2 zeros, okay, and this 0 was missing. That means what will happen? That 0 will actually be a 0 at the origin. Can you sketch the magnitude response? Starts at a point, effect of the first pole, effect of the first pole, gradual droop, again the effect of the second pole. Then you will see the effect of the 0, and after that there is no, basically it keeps going up because basically you're far away from the poles and zeros, right? So basically it does not, you don't see. So here is a ideal, or what starts to look like a low pass filter. Now this does not look like a low pass filter because you allowed low frequencies to pass through, but you're also allowing high frequencies to pass through. So you can now see why a low pass filter typically will have the following response. It will have a large number of zeros located in this region. Okay, and if you have that, then what happens? The behavior looks like this. So now you can see how you can adjust the poles and zeros to achieve the goal that we are interested in. Okay, let's look at another example because I want you to be absolutely confident of what we are talking about. Okay, so I'm going to sketch for you a pole 0 plot. Okay, here is a pole. There is a pole here. Okay, I believe though this is what we have already done. Let's look at this one. Okay, I have a 0 here, I have a pole here, I have a pole here. Okay, so because there are two poles, there should be a compensatory 0 at the origin. Okay, similarly, same at the complex conjugate location also, I have a 0 and I have two poles which are on either side, so there is a second 0 here. Okay, give me the magnitude response. Starts off at omega equal to 0 at some point. You see the effect of the pole, and the effect of the pole is to push it up. Then a sharp change because of the 0. The second pole comes up, and then after that you go far away from the pole 0. Okay, what is this? A notch filter. Okay, so you can see how the poles and the zeros will compensate for each other. Now the same thing, same figure. Okay, let's take this figure. Okay, supposing I had removed the zeros, removed the poles. Okay, no pole here, no pole here. What is the response? So nothing at the origin. Okay, two zeros. Compensatory, there should be two poles at the origin. Okay, so let me use it a different color. So basically these are the zeros. There are two poles at the origin. Okay, now sketch this. You start at some point. Right from there, the effect of the 0 will start to take place, and similarly it will do this. It will not be a good notch filter. And how do you make it a good notch filter? By using the poles, so that you are forcing the poles to push the response up. So basically you're cancelling. So the effect of the pole is to sort of compensate for this, and then you come down and then you go up to compensate, and then so basically this is how you design your LTI systems to get a good behavior that you are looking for. Low pass filter, high pass filter, all of these things can be designed in the way that you can get the response that you want. Okay, I hope you will think about this particular aspect that we have been studying, and study it carefully, and then look at the implications of that.